Hello everyone, I am Moshrefa Sultana Chaity. Today we'll be discussing about Log20 fully automated optimal placement of log printing statements under specified overhead threshold. This paper is written by Zhao. First, we need to understand what are logs. When systems fall in production environment, log data is often the only information available to the programmers for post-mortem debugging. Developers have to rely on logs to reconstruct the execution paths. Here is an example. In this program, we can see that we need to update the max value, and every time we update the max value, we need the value of that. And the programmers has added a log statement here. Now, such log statements are critical in production systems because the only information available in postmortem debugging. That is why the quality of log is very important to guarantee the quality. Now, where should be the log statement? Finding the most informative placement of log printing statement is difficult. Here is an example that the authors have used in their paper to discuss about the log printing system. From this control flow and the program, we can see that this program is about to updating the maximum value. Here in line 2 and 3, they say that if the length of A is not equal to 3, then the program returns error. If there are 3 different values, then from line 4 to line 8, it updates the maximum value, and in line 10, then it returns. This control flow exactly mimics the program. Now, printing the log printing code is a very critical thing. When the deadline approaches, developers focus on functionality of the code. That is why developers need to anticipate the failure. Now, writing log printing code is hard. And also another hard thing is to find the balance between the informativeness and the overhead. Authors have discussed about the related works. They discussed about the Bol-Larus profiling. There has to consider all possible paths. Also, they discussed about Yuan et al. And in this paper, they discussed about an automated error printing error log placement when log happens. Also, one in another paper discussed about the log enhancer that collects the variable values automatically. Authors have discussed about the history of log statements. They showed that in 3 distributed systems, Hadoop, HBase, and Zookeeper, there are total log modifying reversions more than 28,000. They also showed that there are more than 14,000 total logging statements. Finally, the author showed that 42% existing logging statements are modified at least once. And then the author contributed Log20. In this paper, they have mainly 3 contributions. Entropy, a metric to measure the informativeness of logging statements. And then they proposed an algorithm to find the most informative logging placement under the budget. And then a system, Log20, that allows developers to find the right balance. This is the output curve showing the trade-off between the informativeness of the logs and the performance slowdown. Developers can choose the right balance. The code of the algorithm measures how effective each log printing statement is in disambiguing code paths. Here, the authors said that the length should be 3, and for 3 different variables there can be 9 possible scenarios. Now if the length is not 0, length is not 3, then in line 3 the program returns. And P2, P3, P4, P5 are the other possible scenarios. Here, for updating the maximum values that is happening in line 7, for 4, 3, we can see that it happens 1. In P4, it happens 3 times because for 1, 2, and 3, every time it will update the maximum value. And in P5, initially it will update the maximum value. That is why line 7 is executed once. Now, if the programmers are asked to print every time the asked to add the logs, then where the programmers can add those logs. The author showed that if the programmers want to add the log in line 6 and line 8, then what happens? We can see that for P1, there will be no log printing because in P1, the P1, the length was 0, and that is the length was 0, and that is why it terminates at line 3. For P2, P3, P4, and P5, from the previous slide, we have seen that this is how line 7 updates, and that is why every time lines the placement of log in line 6 and line 8 will be printed. Now, from this scenario, we can partition this whole scenario in 2 subgroups. We can say P1 is one placement and P2, P3, P4, P5 is another group. So the path partition for 6, 8 can be the P1 in one partition, and P2, P3, P4, P5 can be another group of partition. Now the log placement strategies. As we have said that placement A can have this scenario, then we can have the information. If the placement would be like this, then this would be more informative. But from here, as we see that the placement is P1, P2, P3 is together, then it becomes confusing. And in this scenario, the authors described about the entropy. Entropy and the H is the metric of informativeness. Here, the large X is all program execution paths observed. The small x an execution path in X. Px is the probability of X occurring in X. As entropy relates on the probability, that is why the authors described about the probability. Now, if we try to calculate the entropy, we can see that if the probability of happening P1, P2, P3, P4, and P5 equal, then the entropy could be 2.32 for all 5 possible scenarios. But if the probability of happening P5 is 90%, then the entropy reduced to 0.65. And if the probability of happening P5 is 100%, then the entropy would be 0. Finally, we can calculate the entropy of placement. Now, if we try to add the log in line 7, that is the placement of 7, then we can see there are 3 partitions. The P1 and P2 where there is no log printing output, P3, P5 where the log printing output is once, and then P4 where log printing output is 3. Then in the first equation, we can, where there is no output, we can see the entropy is 1. And uh, by this scenario, we can calculate the other two scenarios. Finally, the total entropy of placement will be 0.8. Now, if we want to estimate the overhead of the placement, we can see that in these three other partitions, P1 and P2 has the overhead of 0. P3 and P5 has overhead of 7 and P4 has overhead of 3. So the total overhead is 1, that is logs per path. Now, there is a threshold between the entropy and the overhead. And the developers need to decide between the entropy or the overhead. Here is an example. If the threshold value is 0.5 and the log20 generated the placement at 3, then the entropy would be 2 and the overhead would be 0.2. But if the threshold value is 1 and log20 generated the placement 7, then the entropy would be 0.8 and the overhead would be 1. Now this is the developer's decision that which one he should choose, entropy or overhead. The author showed that for log placement, dynamic programming algorithm is the best, because in a brute force placement, the algorithm has complexity of big O of 2 to the power n. The author showed that the developers need to understand the trade-off between the entropy reduction and the overhead. Also, they need to compare with developers' manual placement. The authors propose that it can help debug real-world failures. Finally, the limitation of this paper is that it has obsolete verbosity level, and this needs time to adapt to the workload change. Thank you. This is all about today's paper presentation.